The best models are enormous, too big and too slow to run on a phone or to serve cheaply to millions of users. So, a whole craft exists just to shrink them while keeping almost all their quality. Today, the two main tools, quantization and distillation, how giant models get small enough to actually use. A frontier model can have hundreds of billions of parameters, each one a number you must store and compute with. That means huge memory, slow responses, and big electricity bills, and no chance of running on your laptop or phone. If we want AI everywhere and affordable, we have to compress it. There are a few ways. Start with how a single weight is stored. By default, each is a 32-bit floating point number. High precision, but 8 times the size of an 8-bit one. Across billions of weights, that precision adds up to enormous memory. So the first question is, do we actually need all those bits? Quantization says no. It stores the weights in lower precision, 16 bits, 8, even fewer, rounding each number to a coarser grid. The model gets dramatically smaller and faster because low precision math is cheaper and moves less data. You're trading a tiny bit of numerical exactness for a big practical win. Why doesn't this wreck the model? Because neural networks are remarkably robust to small perturbations. A weight of 0.7341 rounded to 0.73 changes almost nothing. And across the whole network, the tiny errors mostly wash out. With careful quantization, an 8-bit model can perform nearly identically to the 32-bit original at a quarter of the size. The gains are concrete. Quantize a model to 8 bits, and it's roughly 4 times smaller, uses far less memory bandwidth, and runs noticeably faster. Often enough to fit on a phone or a single consumer GPU. It's the main reason capable models can now run locally on your own device with no cloud at all. Quantization shrinks each weight. Distillation takes a different angle. Train a whole new, smaller model from scratch, but instead of learning from raw data alone, it learns by imitating a big, already trained one. We call them the teacher and the student. The student is far smaller, yet aims to behave like the teacher. The trick is what the student learns from. A normal label just says this is a cat, but the teacher outputs a full distribution, 90% cat, 8% dog, 2% fox. Those soft probabilities are far richer. They reveal what the teacher thinks is similar to what. Learning from that nuance, a small student can absorb surprisingly much of a big teacher's skill. The result is a compact model that punches well above its size, close to the teacher's quality, but a fraction of the parameters, so it's cheap and fast to run. Famous small models were built this way, distilled down from larger ones, keeping most of the ability while shedding most of the cost. There's a third tool worth a mention, pruning. Many weights in a trained network are nearly zero, they barely contribute. Pruning simply removes them, cutting the model size and compute with little loss in accuracy. Quantize, distill, prune, often combined, all chasing the same goal, smaller and faster for nearly free. Of course, there's always a dial, push compression too far, too few bits, too small a student, and quality finally cracks. The art is finding how far you can shrink before it shows. For most users, that turns out to be surprisingly far. You can often cut a model to a fraction of its size and barely notice the difference. This is what puts AI in your pocket. Compression is why models run on phones, in browsers, and on edge devices. Fast, cheap, and private, with nothing leaving your hardware. The frontier grabs the headlines, but compression is what quietly delivers AI to billions of everyday devices. So that's the shrinking craft. Quantize the weights to fewer bits, distill a big teacher into a small student, and prune what's not needed. Shrinking models with almost no loss. It's how powerful AI becomes practical AI. Next time, the series finale, from models that answer to systems that act, agents and MCP. See you there.